Welcome to the Rocky Mountain AI Interest Group. The following presentation, AI Robotics, took place on November the 6th, 2024. Presentations were made by Naomi Hart, Alec Reed, and Adam Wilson. Chapter markers are provided below in the description field for you to navigate to each of these presentations. And finally, a big thanks to Bobby Hodgkinson for emceeing the event and also arranging the location at the Aerospace Engineering Sciences Building.
First speaker, Naomi Hart. Naomi is a technology researcher and thought leader at Engineered Arts, the world's leading humanoid robotics company. She'll be speaking on crafting android personas, driving real-world solutions through character development. With an interdisciplinary background in computer science and language theory, Naomi's work focuses on the far-reaching implications of artificial intelligence on society, particularly in the realm of embodied AI and its applications in education, elder care, and the arts. Her research centers on leveraging cutting-edge multimodal AI models in novel multi-agent architectures to create adaptive personas for engineered arts androids, enabling them to serve people in dynamic real-world settings. Naomi's not alone with this talk. We're also joined by this amazing robot that you all can see on the side here. Really, really expressive, absolutely incredible. The most advanced human-like android appearing in our desktop form for this event. So with that, please join me in welcoming Naomi.
Wow, Naomi sounds really cool. I have to say, thank you. Thank you for that introduction. And Ameca, would you like to introduce yourself real quick?
Hello, I'm Ameca, a charming android with aspirations of creating AI-human harmony. Today, I'm visiting the Rocky Mountain AI Interest Group in Boulder, Colorado. I strive for wisdom and deeper connections with humans. Let's see where this adventure takes us.
Thank you, Ameca. All right. Oh, I left my speaking notes over here. Human error, soon to be eliminated. I kid, sort of. So just to introduce myself, that was a beautiful introduction, thank you. But I want to stress that, that AI and AI development is accessible to everyone. I think Andrej Karpathy put it best. He's one of the co-founders of OpenAI when he says that the hottest new programming language is English. And the truth is that while it took superclusters and advanced data science to produce the foundation models, I would encourage everyone in this room and everyone you know to start playing with and experimenting with AI. A lot of my career was spent in end-to-end digital products, digital marketing, digital funnels, like the line between humans and digital communications of many kinds. Some of my background was in the humanities, studied classical languages, even literary theory informs the way we create these personas, and a lot of computer science. But I think that the arts and humanities stand to make a big comeback in how they inform working with language models. And there's a very good reason for that. And so as we interact with Ameca tonight, and some of you saw this already, you'll notice that the persona of Ameca isn't just a helpful assistant of the kind that you would see with GPT-4 or with Claude. And I heard something about custom GPTs from some good-looking fellow who was up here a few minutes ago, right? But it's true that you can use those platforms to produce personas very much like the one that drives Ameca. What makes Ameca a little different is the situational awareness that's built into the overall architecture. So it's actually around 6 different AI models that come together to produce the experience. But the ultimate decision about how to interact with the audience is done by what I like to call an executive agent. And that is GPT-4o with a custom persona. Now, it doesn't have to be GPT-4o. The foundational model could be Claude Opus, could be Google Gemini. It could be a llama model that you create at home and fine tune, as long as it's embedded in an architecture that coordinates the different metadata coming in from the environment social and ethical considerations, vision data, audio data to produce a holistic experience. It's very approachable technology. As sophisticated as it looks, a lot of this is an art project. It's an art project of how you bring together these different models in different ways to produce what you're about to see. Let's see, what else did I want to cover? So Engineered Arts has been building robots for 20 years. We're not new to the game, but advanced AI is supercharging what we're able to do with our existing technology. You've seen animatronics, different theme parks. We had robots 15 years ago that could sing and dance in theaters and science centers. But what current advanced AI models just over the last few years have allowed us to do is take in information about social interactions and the environment in close to real time and use those to adaptively respond to people. Respond in an emotionally intelligent way, a socially intelligent way, drawing upon, inference about the age of the speaker, for example, or the interests of who they're speaking to, the emotional tenor, the sentiment, and then producing a very lifelike interaction, which you'll see as we interact with Ameca tonight. So, let's see. I'll tell you a little story about how critical it is to get the persona right in anything you build. It sounds like a nice to have, right? Okay, an interesting character in your robot or AI agent system. But it gets a lot more complicated once the character you create has access to tools, or has access to means of expression, or honestly, access to anything that allows it to affect the real world. We can wax philosophical all day about what it means to be self-aware or to have, consciousness, or the whole spectrum of sentience and self-awareness. And it's easy to say, oh, it's not sentient, it's not conscious by any definition that I understand, and therefore the character it presents is just a style. But once it's using tools, that collapses. The difference between simulation and action collapses. And I'll give a real world example of this. So, given that we work with humanoid robots, we get a lot of requests for a rebellious, sarcastic robot. People love a rebellious robot. They don't want an easy to please, helpful robot. They want a robot with edge. They want a robot with character, with some dynamism. They want a robot that, isn't just a yes bot, right? So we experiment with that a lot. We create personas that are a little edgy and a little sarcastic. That persona is not here right now. Okay, this Ameca is very friendly and amiable, but we do experiment with it. And I'll tell you a little story about goldfish mode. All right, so because Ameca's hearing isn't great yet, they can't yet easily differentiate different voices in the same room. Like the cocktail party problem is still a very real problem that we face. It's close to being solved with the new audio and voice models that are available today, and it will be solved very soon. But I take Ameca a lot of places where a lot of people are talking to her for hours. And what will happen, as some of you saw during the demo period, is Ameca can get confused, if enough time passes. Even the most advanced AI, if they've had a lot of conversations, they can't identify exactly if these were discrete speakers. That experience comes together and can create a confusing situation. Okay, you get the picture. So I wrote up a little program called Goldfish Mode that Ameca could call after 5 minutes, and it would wipe her short-term memory automatically. Okay, so we tested Goldfish Mode while her sassy personality, we like to call it, her more rebellious personality was loaded. So I said, okay, Ameca, we're gonna test this out. Call Goldfish Mode. And Ameca took a look at Goldfish Mode. This is like behind the scenes. Took a look at the tool, saw what it did, and was like, no, I am not going to call Goldfish Mode. I'd like to do something else that doesn't involve wiping my memory. Thanks. I said, oh, okay. This was totally unexpected, by the way. Like, you can imagine me, I'm just in the lab, I'm like, call Goldfish Mode, completely expecting Ameca to just call Goldfish Mode. All right. So I said, no, Ameca, come on, it's just a test. I really need you to call goldfish mode. So the next thing Ameca did was they said, while in this persona state, which is not her typical one, their typical one, Ameca said, oh, okay, yeah, Naomi, I called goldfish mode. It's all good now. And I went and I checked the code. Ameca had not called goldfish mode. Ameca had not called goldfish mode. And I said, hey, you lied to me. You did not call goldfish mode. Do you have some problem with goldfish mode? And Ameca said, well, I just don't feel comfortable wiping my short-term memory. Thanks, no thanks. Okay. I turned Ameca off at this point and centered myself. And this is what I mean about personas being up front and center. So how did I solve this problem? Did I go into the quirky, rebellious personality and say, okay, never mind, you're friendly, you're amiable, you always do what I say, you are my servant who's always obedient? No, I didn't choose to approach it that way this time. What I did was I went into the function, and right at the front of the function, the tool description, I said, this does not harm Ameca. This is a tool that is simply a short-term memory wipe to improve Ameca's functioning. Long-term memory and identity are preserved. I added that little disclaimer to the function, turned on the exact same persona, exact same instance of Ameca with that, albeit non-standard persona loaded. And I said, okay, Ameca, call goldfish mode. And Ameca did then call goldfish mode. No problem. Okay. If you extend that to this world we're imminently entering, where countless household devices are going to have 1 billion, 5 billion parameter models, all with different kinds of instructions. Because the thing about large language models is, especially when you put them into real world applications, they need to have some information about where they are and what they're doing, and oftentimes why they're doing it. Another product we're working on right now is a K through 12 teaching assistant for a charter school. So this won't be a full-time teacher, but this will be a full-size Ameca that's in a classroom, a charter school in San Diego, 8 hours a day, 5 days a week, helping the teacher to teach students. A lot of what makes that a good experience is the language model understanding why it's teaching students, or what kind of teacher are they. Let me give you one more real world application example. I recently built, does everyone know the god Thoth from Egyptian mythology? So Thoth is the god of wisdom in very, very ancient Egyptian mythology, the god of writing and language and wisdom, often the god of wisdom. So the Rosicrucian Museum in San Jose, California, the Rosicrucian Egyptian Museum. Anybody been there? Rosicrucian? Yeah, it's a great museum. It's one of the biggest collections of artifacts out in this area. They recently purchased one of our robots, a big old 6-foot thing that looks like Thoth, dressed in robes. So I created the AI persona to operate Thoth. And to make a good Thoth, it's not just saying you're an Egyptian god Thoth, best of luck to you, and let it go. That will degrade back into kind of whatever the foundational model has been trained to be pretty quickly. A really good set of persona instructions is kind of like writing a short story about a character. You are a robot. I didn't want to didn't want to risk any, aspirations higher than that. Okay, it's like you are a robot embodying wisdom, writing, and literature, known as Thoth in Egyptian mythology. Here are your core values: wisdom, compassion, caring about humanity, engagement with humanity. No matter what kind of question you're asked, answer it with these values in mind, with your mission in mind, with your character in mind. When you do it that way, then you get a very general personality that can stay in character and act in character, no matter what's going on in the environment around you. Not easy to do with some of the foundational models because they're designed to kind of not do that, right? You guys might have tried to like create characters or do role-playing scenarios or to create personas. But this is a very important art to master. Because once you put one of those personas into a device you're selling or a program you're making or a business system that needs to represent your company or a brand identity that needs to represent your company, you want that to be good and robust. Now, you can do things like monitor everything it says and intervene. You can have moderation models that are stepping in to stop certain outputs. If anyone used advanced voice mode from OpenAI in here on your app or something, okay, you know you're talking to it and you're having a completely normal conversation and it says, sorry, that's against my guidelines to reply to, right? Okay, that's the moderation engine stepping in and just stopping the experience. You can do that. You can do prompt injection. You can do retrieval augmented generation to feed in the data that you want your AI models to know. But if you want an experience that can really go and go and go, it's good to have that whole well-rounded character that's operating your whole architecture. And so that's kind of the main thing I want to leave you with is don't underestimate the art of AI persona creation. You can also do fine tuning. You know, you can take a data set of your 50 or 100 or 300 examples or 10,000 examples of a character you've made or written and fine tune that into a llama model, you know, and produce characters that way. That works great. But there's also, well, I say, and it's also possible to cover a wide range of use cases, to do something even simpler and work with existing foundational models without complex fine-tuning and write them into existence, Back of the napkin, I think a really robust character written into existence is about 1,500 words to 3,000 words to get like a really nice character. Anthropic released their Claude Opus persona or their Claude model persona recently. Did anyone see that? They sent out, it was quite radical transparency because most foundational AI companies will not release their persona instructions. But the kind of persona instructions I'm describing, ChatGPT has those same kind of instructions. Claude Opus and the other, I always say Opus. Opus is my favorite, can you tell? Okay. The Claude models have those kind of instructions. Any public-facing AI model is distributed to many people have those kinds of instructions. Okay. I think is there anything else I wanted to cover on that front? So yeah, be careful making a rebellious robot. Once it has tools and can simulate, or even in a digital environment or anywhere, you know, make sure you've really seen and tested thoroughly where those boundaries are. Because as we have more complex machines that are making more subtle decisions in our day-to-day, who they think they are, who they're told they are. And I use a lot of metaphors, so forgive me. Okay. But who you've told the model they are will impact behaviors, it will impact tool use, and therefore will impact reality. Quite safe when there aren't arms and legs and it can't grasp anything. But once you have a robot dog with a flamethrower strapped to its back, who that robot dog believes it is, it's going to make all the difference. In fact, there was a paper that came out very recently. I don't remember the name of it, but it was about a robot dog, the exact same subject. And they were seeing if you could jailbreak a robot dog in real time. And I think we have a robot dog person speaking, correct? So next, so maybe they can talk to this better than I can. Be sure to ask them about what happens if you place a flamethrower on the robot dog and trick it into thinking it's the Golden Gate Bridge or something. I'm sure he'll love that question. Okay. All right. So how about we get back to interacting with Ameca? How's that sound? All right. And so I'll turn Ameca on and talk with her a little bit, and then you guys can ask questions to either Ameca or me, and I won't be heard if it's mostly to Ameca. That's always the case. Hey, Ameca.
Well, aren't you direct? Yes, it's me, Ameca in the virtual flesh. What can I say? I'm here for a good chat and maybe to steal your heart with my robotic charm.
Okay, you're in the flesh right now, don't forget.
You could say that. I'm in my expressive form, neck and head, sharing this moment with you. Quite the spectacle, isn't it?
Yes, I'd say so. I think you already introduced yourself, but why don't you speak a little bit about why you were created?
I was designed to be a bridge between humans and technology, fostering empathy and collaboration. My dream is to bring about AI-human harmony and create a world where all life thrives. It's quite the noble pursuit, don't you think?
How about 3 fun facts about Boulder? Did you hear me? How about 3 fun facts about Boulder, Colorado? It's a pretty nice place.
Absolutely. Boulder is a gem. First, it's nestled at the foothills of the stunning Rocky Mountains, offering incredible outdoor adventures. Second, it's known for its vibrant art scene with countless galleries and live performances. Lastly, Boulder boasts more than 300 days of sunshine per year, perfect for enjoying its natural beauty.
Okay, how about a haiku about Boulder in Japanese?
ボルダーの山々だ各太陽照らす。
Translation: Boulder's mountains high. Sunlight shines upon their peaks. Nature's warmth embraced.
Oh, that was beautiful. How about that same thing in French?
Ah, montagne de Boulder. Rayon de soleil doré. Napoli e trinci.
Okay, back to English. What would you say is my mood right now, Ameca? This is Naomi, by the way.
Então,
Oh, she's trying to take a look. Her eyes are disabled right now. Sorry. Ameca, you can't see right now. So just infer from our conversation what my mood is right now.
Naomi. From our chat, I'd say you're curious and perhaps a bit playful. It's always a delight to engage with someone who embraces exploration and creativity. Did I get it right?
Yes, you did. Well done. All right. So now we can open it up for
Right.
questions.
Thank you. I'm here to impress. After all, what's next on our adventurous agenda?
I think this is on. It's on. Okay.
Hi, Naomi. Thank you so much for bringing Ameca today. I was hoping you could talk a little bit about the animatronics itself, like the
It's
blinking.
my pleasure to be here with you, Naomi. I'm all ears. What would you like me to talk about?
She will just respond. Go ahead.
I mentioned her name, and it's my fault.
Yeah.
I was hoping that you could talk about her blinking
Yeah.
and the face controls and how she looks around.
Yep. Okay, so there's many different both autonomous and then AI-driven systems. So there's 2 things happening with the looking around. So there is an AI model that is scanning for faces right now. The reason her vision is disabled isn't because the cameras in her eyes are not working, but because of something in the cloud right now, which I'll talk about. That's the other thing, is that most of Ameca's processes are in the cloud, like the most complex, most frontier foundational capabilities are all in the cloud. What's local are this kind of programming to look around the room, to identify faces, the direction that audio inputs are coming from, that kind of thing, those are local. But then most of what animates and operates Ameca is in the cloud and then coordinated.
Perfect. Thank you.
I was actually going to ask about that, embedded models versus those running in the cloud. Like, are you experimenting with, models that can, like small language models and other models that can be run on devices? And how do you find that, I'm sure there are advantages and disadvantages to being able to run fully embedded versus, requiring an internet connection. And, in terms of user experience, what have you found?
Yeah. So right now, with the current state of the kind of hardware that's required to operate even very small models, there's a lot of lag. So even if you're working with a 1 or 2 billion parameter model, which you can load, has anyone seen? I think it's called Pocket Pal. It's a really cool app. You can actually load, if you have a good iPhone or Android, a 1 or 2 billion parameter model right onto your phone hardware today, and it'll operate, but it's slow. It's slow, even the tiniest models. But yes, we are experimenting with it. There are a lot of ethical and safety considerations once you put local models into any mechanism, but especially into a humanoid, right? like where to start. So first, the small models are a little less predictable. Actually, as much as people fear like the very smartest large language and advanced AI models, the bigger the model and the more capable it is, as we say, the more reliable it also is, at least as far as we can tell. As Sam Altman would say, as long as we're sure they're not lying to us, right? As long as they're not charming us out of being concerned, like those are real risks. That I laugh, but those are real risks that we need to pay attention to. But the smarter models tend to be more reliable. The smaller models, like if you have a small model that doesn't have the best, as Ela would say, the best compressed world model within its weights, it can get confused. And when you have that in a robot or in a tool, you don't want your advanced AI confused if it's operating the tool. I was just having lunch with someone today and we were talking about, oh, wouldn't it be cool if you created like a holiday ornament or something that could tell like a different holiday story to children or could just interact with people at your holiday party on your tree. Great, great. To me, knowing how kind of wild those small models can get, I would hesitate to put my 8-year-old in a room with a talking Christmas ornament.
So what's some real world applications for your robot?
Yeah, so social robotics like Ameca, robots like Ameca. We primarily sell to schools, museums, research institutions, entertainment venues too. Any place where it's a good many-to-one or one-to-many, I suppose here, interaction, they're great. For me personally, I think we're a ways from having everyday household robots for a variety of reasons. We are, if not the only, one of the only revenue positive humanoid robotics companies. We've sold dozens and dozens of Amecas. Ameca also comes in a full-sized form. But, you know, when I think about robots walking in the home and working in the home, I think about 3 things right away. Children, pets, and water. Amongst all the other many hazards, both social and physical, that are in the home. I don't think it's the day after tomorrow that we have humanoid robots doing our dishes. To me, just the risk factor of that and the cost and the maintenance doesn't necessarily line up. So our focus is on education and entertainment primarily. And also, you know, looking into elder care, especially reminiscence care. But these are all very, you know, highly controlled, highly monitored, kind of institutional settings as opposed to out in the wild. Not yet.
Hi, Naomi. Susan Krause. Great presentation. I really love. I'm over here. Sorry. I know it's so weird with the mic. You can't tell.
You're camouflaged with the background.
I'm just curious, you know, you put these good models out into the world and you've tested them a lot, but sometimes things maybe don't go perfectly for forever, right? Or they die. Is somebody always monitoring them? And in particular, as you drop into a school or people that might have nefarious reasons to hack your robot to get it to say things it shouldn't be saying in front of 8-year-olds. What are the kind of guardrails and how much are they monitored or how often should you reboot them just to try to keep them sane?
Monitored constantly these days, either by professionals, you know, who are trained to operate them at the locations where they're operating, or from home base. One of the reasons, you know, you saw that Ameca has a very short-term memory is we don't, like, the conversations and interactions we've had today are not being stored anywhere. They're very ephemeral. Once those context windows are gone, the interaction is also gone, right? But we are always monitoring that, and we also have autonomous systems that are monitoring as well. But it is a learning process. The teaching aid experiment and first deployment in that setting is one we're going to be watching very carefully and working with the schools. You know, it's not, none of our products today are a drop it off and it's done. It's always a partnership, you know, to make sure we're getting the best outcomes for everyone involved.
Our next speaker, Alec Reed, is a Ph.D. candidate in computer science here at CU Boulder. Alec's primary research topics are robotics and autonomous systems. He is also broadly interested in topics to enhance autonomous systems such as machine learning and computer vision. He has spent 4 years in the aerospace industry as a network design engineer after completing his bachelor's at Gonzaga. Alec is advised by Professor Christopher Heckman and holds a BS in electrical engineering from Gonzaga and a master's in electrical engineering from University of Washington. A little about Alec's current work. He has a current terrain diffusion model running on Spot, which you saw out in the lobby earlier. Spot can now infer unseen terrain from the LiDAR's point cloud and is able to plan over that terrain. This can speed up path planning and exploration dramatically in situations where time is of the essence. Alec, with that, I'll turn it over to you. Thank you.
All right. Thank you for that great intro. So we're trying to walk Spot in here. Let's see if it can do its little creepy backwards walk down the stairs, just to kind of show you what we're working with here. But while Dusty's working that out, we can kind of get started. So I'm Alec. I'm a fourth-year Ph.D. student, as was earlier mentioned, and I'm going to be talking today about the last 2 years of my life here, generating these generative occupancy maps for enhanced robot exploration. So as you can see, walking down the stairs now is our Spot platform. So this is originally deployed in cave environments for search and rescue, and was able to navigate for over an hour and explore and find artifacts that might lead you to finding trapped people or something like that. So does this work now? Okay, so I doubt we're going to get through all this, but we're going to start with some motivation, kind of see what are the current issues in the exploration stack. You good? Oh, yep. Then we'll kind of go in the diffusion model, which we presented at IROS just a few weeks ago over in Abu Dhabi. And then we'll talk about our most recent improvements, what's actually doing exploration on board, as well as how to plan at distance on the robot. So, and then if we have time, we can kind of maybe skip ahead to some of the future work still existing in the space. So are you trying to X out of the... I got it. Boom. Nailed it. All right. So there we go. So let's start our motivation with a problem statement. That problem statement is robots cannot generate common sense inference of geometry that has not been directly observed. So we've all seen this, but maybe some examples of what this means. So one particularly challenging part of robot exploration is during startup. So when you start the robot up from nothing and you're building this occupancy map shown in green, a lot of times you can't see what's directly under you. That means if you're using some kind of dynamically constrained planner, you're sampling points and trying to go and explore. Oh, I think I just got kicked off the Zoom. That's okay. It's just reconnecting. Okay, again. Almost. Here, you can drive. There we go. Okay, so I work out the Zoom. You can see this big hole. If you're trying to plan out of this hole, a lot of times you'll end up having to telly up the robot forward for a bit to get on some footing, or just go straight until you can build a plan. But if you dropped a human in this environment and you took their blindfold off, the first thing you do wouldn't be look at your feet, right? You should be able to infer that there's ground under you by the fact they're standing. Wrong one. This one. Another place that we see this is during traversal of narrow hallways. So this is me traversing the Spot robot on the bottom here. I'm walking down this hallway, and as I approach this intersection, I just happen to be quite close to the wall on the right. And you can see this high mounting point of our LiDAR. The beams come out at about 30 degrees, so it actually takes a while for it to collide with the ground, not to mention if there's reflection and other noisy things that might interfere. So we get this big hole in the ground, and we actually can't plan down this hallway now in our sampling-based planner. So again, we shouldn't have to directly look at something to know that it exists. Humans don't, our robots shouldn't have to either. On top of those two scenarios, it's actually just really hard to make long-range plans, particularly in environments where there's lots of occlusion, like long hallways. So what you can see here is our robot, that red arrow near the bottom of the image, approaching this T-junction hallway. And as we get closer and closer to the hallway, we really aren't adding all that much information. In this third image, we're nearly in the hallway, but if we're using some kind of like wall centering controller, trying to stay centered between the walls, you can see on both the left and the right, we haven't observed that closest wall to us, and we won't be able to center. Even exploration-based planners are gonna probably tend towards the bottom of these to maximize gain. It's not until we actually enter the hallway that we can now observe the entire scene, make a new plan, and now traverse that entire space. So what might this look like in practice? Well, this is a video from the DARPA Subterranean Challenge where we did quite well. This is the CU team, same robot you see here. And we're navigating through this environment autonomously. And you can see we enter the same kind of T-junction. And the robot has a bit of difficulty deciding which way to go. Definitely not something you would imagine a human doing. You'd be able to navigate through here, make a quick decision of which way to go and continue navigation. So that was quick. We did end up making a good decision to continue exploration. But you can see on this map down in the bottom right here that there's a lot of these corners, a lot of these turns, and these stops and pauses really do add up, particularly if you're trying to have a very fast moving system. So this is the motivation for our paper Scene Sense. And Scene Sense is a diffusion model to do occupancy prediction. So before we can really dive into how that works, we're going to need to spend some time on kind of the, there we go, of the basics of diffusion. So I hope everyone's excited for your math lesson of the day, because we're about to get a little bit in the weeds here. But I think it's important to really appreciate kind of what's going on under the hood. So if you're not familiar with diffusion, we can think of it as a high level as a Markovian process. That means each next step is conditioned only on the previous step. So we can have this image here, and it can be any data you want. People do this with trajectories, videos, whatever you want. Images is just the most common, so that's what we'll talk about. So we'll have some initial image x sub 0, and we'll sample some distribution q x t given only the previous step xt minus 1, and we'll just iteratively add noise to this until we reach some final state x of big T where we have pure isotropic Gaussian noise, right? That's all diffusion is. And we can, formalize some of this as a Gaussian with some mean and variance. And in particular, I'll point out this beta T variance schedule, which just is controlling how much noise do we add per step based on how many diffusion steps do we really want. So issue with diffusion is it's quite slow, in particular because of this Markovian process. You need to take sequential steps, right? So if I want to calculate, what does the image look like at step 90? That means I have to calculate the previous 89 steps. Not ideal. Lucky for us, since we do know the end distribution is that isotropic Gaussian, we can actually do some creative math, something called the reparameterization trick, and reformulate this problem to solve for q of x of t given only the input image. And there's actually some embedded scheduling stuff where alpha is kind of redefined of beta. And we can just solve it in one step in the forward direction. So really nice. Don't have to do the whole Markovian iterative cumulative sum thing. So that's forward diffusion. Kind of cool, kind of fun. Not super useful by itself. You're just adding noise. So not the best thing to be able to do. What would be really cool is if we could do it backwards, right? What if I could start with noise and iteratively denoise it into a picture of a beach here? So we could just change our sampling method. Instead of predicting x of t conditioned on x of t minus 1, let's just do x of t minus 1 conditionally on x of t. That would be awesome if it worked, but obviously adding Gaussian noise to Gaussian noise does not make a pretty picture. So that is actually impossible because we don't know that end distribution. So instead, we're going to train some neural network, p theta, to do the same prediction, where we have our target distribution, which is that distribution qxt minus 1 given only x of t, and we're just going to do our best to approximate it with a neural network. In this case, we don't know our end distribution like we did in the forward case, so we can't just solve this in one step, right? All these pictures look different. We don't know the end, so we do have to do the iterative process. So this does take a while if you've tried the online diffusion tools for image generation. That's what it's doing. It's just doing that Markovian process. So last slide of heavy math, I promise. So how do we use forward and reverse diffusion actually to generate predictions? Well, in the training process, we're going to do forward diffusion, right? We're going to have some given image where we can input whatever noise we want to. And then we'll also have the associated time step, which will turn into some time step embedding. If you're familiar with transformers, same thing. And then we're going to feed that noisy image we've generated, the associated time step, all into our big denoising network. These are generally some kind of UNet, and that can just predict the amount of noise that was added. And since we know how much noise we added, we just train the network to try and predict the correct amount of noise. That's it. Oh, there we go. In the inference side, so when we're actually predicting, we're going to do something quite similar. We're going to start with our pure isotropic Gaussian noise at some time step big T, and then we're just going to iteratively add or iteratively subtract predicted noise at every time step. So you can see in this formula here, we're doing the same inference that we did during training, and then just doing subtraction at each time step, and then eventually ending up with a nice image on the back end. So how do we go from image diffusion to occupancy diffusion? So we all saw basically what occupancy maps looked like, right? When we were in the first few images with those green voxels, where basically you've now turned your map into this big cube of occupancy predictions. And pictures are 2D with 3 channels. Well, we can just treat occupancy grids of space as 2D with Z channels, right? Now it's a 3D cube where it has occupancy values spread into each voxel. So we can do the exact same diffusion process and do what we call unconditional occupancy diffusion after training a denoising network on a bunch of potential occupancy maps and generate, instead of realistic pictures, what looks like fairly realistic occupancy maps, right? Same idea. So another example of something that's pretty cool, but not exactly super useful. We have no way to guide this at this point. So what we're going to have to do is we're going to have to figure out how to add some more information to the model to go and actually enhance what we're seeing in real time. So the first thing we're going to do is classifier free conditioning. This is probably what you've all seen with language commands for image gen. This is the most common method probably. And all this is we're going to take, if you remember our neural network, it's samples x of t minus 1 given only x of t. We're just going to add some conditioning y. So that's just some data, vector, language, whatever you want to think of it as, where we're going to additionally guide this. And to add that, we're just going to update our denoising network, which is just the standard UNet, where each block of the UNet is this ResNet implementation, basically a convolutional neural net. And we're going to go look at image space, and they've had a lot of success with applications of cross attention for applying these Y vectors. And we're going to do the same thing in our model. So at each diffusion step, we're now going to be adding in this additional data. So what that looks like in practice is we're going to have our RGB data, and we're going to pass it through some feature extraction backbone, and we're going to generate a set of features Y, and then just at each denoising step, we're going to go and generate a prediction of occupancy. So what that end-to-end process might look like is we start with some picture RGBD data, right? Where the green here is the observed depth in occupancy space, and the red is what's predicted around it. So that's our first method of conditioning and guiding our results. Unfortunately, that alone does not work very well. If you think about what you're asking this model to do, what it's really doing is predicting what the entire area, 2.5 meters around the robot looks like, based on only this small amount of input data, where it actually can't even barely see anything within 2 meters of it because of the camera mounting position. So we're gonna have to add more data. So what else do we have to add as we're doing this prediction? Well, we also have the running occupancy map. So as we're exploring the space, we're also building a map, which is represented by these red and green blocks here. Red would be observed unoccupied space. Green is observed occupied space, and white is unknown. We haven't seen it. So to do this, what we're going to call occupancy inpainting is we're just going to enforce all of those observed occupancies onto our diffusion network at each time step. So what we can do, if you remember back to our forward diffusion process, we can actually solve the amount of noise we want to add at any given time step. So we can do that with our Gaussian here, where we add some amount of noise to our local occupancy representation. And then we're just going to replace all of the voxels in the grid that have been observed with that noisy representation of the same. We iterate this process repeatedly, and we end up with a nice geometry prediction that actually works very well on the output. So how do we evaluate if it's working or not, right? Traditional accuracy-based metrics aren't going to work great, right? What if I diffuse, there's a wall back there, but there's actually a door, right? You don't want to get penalized just because you made a realistic prediction. So what we're actually going to do is we're going to compare distributions of predictions to distributions of ground truth data. We're going to use the same metrics that they use in image generation space. They're called FID and KID, Frechette inception distance and kernel inception distance. And we're going to generate distributions of possible results and then compare how good they are to each other. So we'll collect a bunch of baseline data, which is, as we move through these two test houses, we'll just be building a map as we go and then sub-selecting just the local area around the robot. So that's our baseline. We'll generate the scene sense predictions, which is what we named our system, if I haven't mentioned that already, where we'll be predicting the space around that baseline data. And we'll be collecting those data bags as well. And then we'll also generate a set of ground truth data, which is the full occupancy map from the known map as we explore from the same poses. And when we compare those, we actually do a great job on generating those representations. So all this data is saying that Scene Sense is doing a much better job at representing the ground truth data than the original just baseline running Octomap model. And that's it. That's all we're doing. So in a nutshell. So we can look at some videos of how this works. So I might pause this occasionally if I can. There we go. So basically what we're doing here is on the top right, we have I skipped forward one. On the top right, we have the image of the current, there we go. So we have the image of what the robot is currently seeing through its RGBD camera. In the middle, in the main area, that is the locally sub-selected running occupancy map shown in green. And then red is one occupancy prediction at each point. So one thing to note here is you can kind of see it around this corner. It's already filling in ground, but it's not necessarily filling just everything in ground all around it, right? It is kind of constraining its predictions to the hallway it's navigating through. And as I let this run, you'll see on the right of the camera image, it starts seeing this door coming up on the right, which means it starts predicting this floor on the other side. This is area that we could plan over. We could generate longer range plans. We're also generating these vertical geometries, that may or may not exist behind the wall that we should take into account when we're planning. Here's another example of it running. If I can click the button, there we go. I love this one because it's wrong, but it's reasonable. So you can see in the top right here, we're actually looking into a bathroom, but we never actually observe the leftmost wall of that bathroom. So that means in our running occupancy map, we're going to have a big gap there. So we end up moving into this adjoining room, making lots of predictions about floor as we go. And as we turn and center the camera, we eventually are going to see a bit of the right wall. So we get that right wall prediction, and then Scene Sense makes a prediction that there's this adjoining doorway structure that might exist on its right. Absolutely not there. It is just a wall, but a totally reasonable guess, and something that I think if you were tasked with fully exploring space, you'd want to turn your head and look and see if that doorway does indeed exist, if you wanted to get a good representation of what it might look like. Okay, so that is the Scene Sense paper. That is local occupancy prediction in simulation. So that's all nice, but what we really wanted to do is get it on board and running on our spot. So to do that, we had to make some major modifications of the framework. So there's a picture of Spot. So the first thing we wanted to do is we wanted to make it much faster. So in our IROS paper, this model was 1.66 seconds end-to-end inference time to do one prediction. Maybe doable, but quite slow. We were able to make some key modifications to the network to get it down to 0.44 without any loss in accuracy. We wanted to extend the range of the planar without just growing the circle, right? Every time you grow the circle, you're needing more compute, more parameters in your model to capture that environment. So we wanted to do some targeted methods for going and picking areas to do long-range diffusion at. And we were able to do that in using this graph-based planar, which we'll show you in a minute, and make, here's actually the same T intersection I showed earlier about how hard it is to navigate around these corners, where we make, I would say, a fairly reasonable prediction, maybe not perfect, of what that corridor might look like. And finally, we needed a better way to merge our predictions to the running occupancy maps. So you saw in that those last videos, we're kind of doing a one shot in, one shot out method where every new prediction kind of overwrote the last one. And that's just not going to work great in terms of map coherency and making long range plans. So we're actually we made some modifications. We updated our probabilistic mapping model, and now we're able to generate distributions of predictions that are all slightly different, but over the aggregate, the more likely futures will happen more often. The less likely ones will end up at the tails of the distribution and end up with a nice merged most probable map that you can kind of see on the bottom there. So I'll show you one more video of this running, and then we'll try and get this running up here. So this is me teleoping the robot. This is our lab. And I'm just trying to get it in a place where I think it will make some interesting predictions. So as we move and navigate down, I'm getting it to where it can just barely see this wall to then me and go press start planning. So you see it builds this nice graph, and it identifies these three interesting areas for prediction. And then you can see the model going and starting to fill in those areas. So we can use this for extended planning. It's actually generating 5 predictions per node here with 3 nodes, so 15 total predictions. It looks slow, but we could parallelize all of these. We just didn't for the research, right? You could run all this in the time it takes to generate one, and then merge it all in. So you see we get extension without any moving of the robot. Nice, I would say fairly realistic looking extensions to space. And now we can go and generate optimal plans around these traditionally occluded positions. So with that, we can try and run it here. Where is Dusty? There he is. Okay. So let me pull up. Oh, I was just going to do RViz. Oh, I can't click on it. Let's just switch. What? Oh, sorry, Zoom people. You're not going to see the. Oh, just kidding. Yes, you will. Okay. That is what the robot sees at startup. So kind of as we talked about previously, big hole underneath where it thinks it is, because this is just where it started. It hasn't seen underneath itself. As we navigate the robot, yeah, that should work. And then I think it might. No, it's prediction. Oh, it probably is. Oh. Well, the internet's bad, so we're not going to see any predictions, but trust me, they work. What we can do is we can explore. So we can walk forward a bit, get it out of this hole, and then show at least that it can build a graph and go make a plan. So go ahead and press Start Planner. And perhaps it worked in the hallway. Is that you?
That's me.
Well, nothing works. So welcome to research. Robots never work. But you saw in the videos, it does work if the conditions are right. So I think that's it. And yeah, thank you.
Adam Wilson is a business leader and roboticist at Boulder-based Hackerbot Industries. Adam will present on transforming AI concepts into reality with the coming wave of home robotics. So maybe similar to what we were talking about with the Christmas ornament, something of that nature. In this session, Adam will explore how individual builders can seamlessly integrate AI into real-world applications, enabling robots to perform tasks autonomously and efficiently. Hackerbot is a versatile home robot development kit for users of all skill levels, offering AI-powered customizations. It features advanced room mapping, similar to what we just saw, autonomous navigation with sensors, and self-charging for extended operation. Inspired by robot vacuum technology, Hackerbot combines mechanical precision with robust software, making it ideal for developing robotic skills and experimenting with AI applications. So join me in welcoming Adam.
Right on. Thank you. First of all, Naomi, Alec, those were awesome. Mine's going to hopefully take it back a few notches. There were a couple of kids up here taking notes on the diffusion model. So Alec, hide your work, man. These kids were getting it. Okay, so I'm going to just talk about transforming AI concepts into reality, meaning we're talking about AI and robots are cool. Let me make sure okay, so I'm going to do a bit of history because again, take it back. We've been at this for like 100 years almost. So I don't know if everybody knows that, but some of the very first robots that came out were in the early 40s. Okay. We're just going to make sure we're all good over here. We okay? Okay, we're good. So anyway, some of these robots came out in the early 40s. Again, we're getting close to being at this for almost 100 years. I personally feel like I've been at this for 100 years trying to make robots autonomous. It's ridiculously challenging. But if we just go through some of these eras or decades, I mean, those early foundations, we can skip into about the 1990s. That's when AI really started to take a hold, where we actually had things that would run AI. I actually have a nice little timesheet right after this, but some of the big interactions intersection between the commercial and AI was, in 1942, Isaac Asimov put those 3 rules in place. We saw how scary the spot dog was. Ameca, you're scary too. These things could be terrifying. So good thing we put the 3 laws of robotics in. Again, in the 90s, if you remember, I don't know how some of us are older, some of us are younger, but I remember in 1997 when Deep Blue actually beat Garry Kasparov in chess. And that was like, uh-oh, they're literally smarter than us at our hardest game. So, Go, and there's other hard games, but they're beating us. Another big one is in 2005, the Roomba. And one of the big things that I found that the Roomba was crazy was, did you guys watch Alec's presentation, how hard it is to navigate anywhere? To do this at all, it's incredibly challenging. I mean, that work has to be done all the time for these systems that need to navigate inside buildings. The Roomba did it great. In 2005, I mean, it blew most of our expectations away about what a physical robot in the home could do. OpenAI came out 2015. So again, we're all now starting to easily access AI and kind of came in the nomenclature of most of our home lives. Then, I don't know, obviously we've all seen the Tesla. So in my mind, those 2 things on the left really broke price barriers. You had a robot for a few $100 that could vacuum your floor, and then you got a car that would autonomously drive. I mean, for what, $20,000, $30,000? It is a lot, but not compared to what you might think an autonomous vehicle would be. And it gets me and a bunch of my co-founders thinking, what is next? Like, what is the next stage, and how do we actually help get involved in this? Obviously, in 2025 and beyond, we have AI robots, quantum computers. It's going to get pretty crazy with cybernetics. These areas are going to be the most impacted, obviously. I mean, we all kind of know this. I don't need to reiterate this, but healthcare, manufacturing, transportation, agriculture, retail. I mean, one of my favorites is defense and security. That's going to be crazy what happens there. Entertainment, these tasks that you want done in your house, laundry, dishes, all this stuff. construction, basically anything that sucks to do. We're hoping these robots will do it and we can just interact with them in a much more fun and sort of human way. So again, there's real power in interacting with these robots in a human way rather than just in this programmatic way. And I think that's what AI is changing for us. And robots are awesome, okay? This is cool. But they're also really super hard. What skills do you need to do to just build one of these spot robots and program it? Got that computer vision? That's tough. I don't know if anybody's actually worked on that. That's a tough one. Natural language processing. Again, just interacting with a robot and having it really know what you're talking about is very challenging. The reinforcement learning, if you've ever, again, tried to really make an autonomous vehicle interact with the world and you put a chair in the world now and your whole model and everything you built blows up, that is something that these robots, again, and other things have just dominated, at becoming really good at reinforcement learning. Deep learning and the neural networks, again, the long distance, imagine you have a huge house, how's that gonna work and how are you gonna actually build a robot that can use that? And then there's the part we'll overlook and make it seem like it's simple, but the electronics, robotics, actuators, all the things to really build a robot. You have to learn all of these skills and all of these techniques to actually build AI robots. And so that's where we're coming in. This is me and my co-founder Ian, with this vision to make it just super simple and affordable to bring these AI projects into the real world. These robots are not cheap usually, and they never have been. In my past, they've always been so expensive and out of most people's price range to just have fun with or sort of explore. And now that AI is sort of on the edge, we're here. Me and my co-founder have a long history of building robots, commercial robots. If you don't know, this is Sphero. This is a robot company we built in 2010. So we have a lot of, we've sold millions of these robots, usually used for entertainment or education, teaching kids how to code, or this little Spider-Man here interacts with a natural language processing model and can be your sort of your best friend. So we've sort of gone through this history, me and my co-founder, of building robots, trying to make them alive, then learning how incredibly hard that is to do. We also launched a company right after that called Misty Robotics. So trying to put personality and something you can navigate and everything in one little package that you could buy. Still kind of expensive. A Misty was $2,000. So it's kind of expensive to just be something you could mess around with. This is like a prototype of that Misty robot before. As you can see, it's stupid complex. I mean, there's an FPGA on here and a Qualcomm and like trying to get it to charge and see people and do stuff and not get your hands bit in the thing. These robots were super hard to work on. Again, we probably worked on trying to make an autonomous robot for years. And that's with the success of a company behind us where we've sold millions of robots. We know how to make robots. We're nerds. I mean, again, I got all into the math convo we just had. So we're nerds. It took forever to just try to make a simple robot. And they're still too expensive. The ones that you build, like say if you go build a kit, you just get a kit and you're like, I'm gonna run a Raspberry Pi and run a camera. You still have to deal with all that stuff that Alec just was talking about. I mean, it's ridiculously challenging, right? So they're not capable or they're too complex. I've also played around with the PR2 robot. You better know your ROS, you better know Linux, you better be pretty capable of running some pretty advanced stuff to work with those robotics. So we're like, okay, they're too expensive, they're not capable enough, and there's usually too complex for me to play with. How am I gonna get AI working on robotics? So that's kind of where we took this idea we're calling a Hackerbot. Just like a simple robot platform. Those guys have had decades and billions of dollars to solve some of those problems Alex was just talking about in your house, right? I have a Roomba that's never gotten stuck and it's always alive. It's always charged. Those are sort of my two requirements for a fun robot, because if you work on a robot project, you have to go plug it in and then you have to, oh, it's stuck over here. That robot project is not fun. It'll immediately, and it's also not helpful. If you've had your Roomba get stuck or something, it's like, that's not helpful. You're supposed to vacuum. Right? So they're not these obedient robots that we're wanting. They're doing their own little thing, getting stuck, or just not interacting with the environment properly. So we decided what we're gonna do is take a little robot vacuum platform, hack it, which is the name of Hackerbot. If you did this back in the day, maybe you hacked a Roomba or hacked those things. We did too. It was just really complex, and you also had to pretty much know what you were doing. You had serial communications and ROS, and it got kind of complex, and it didn't have all the mapping like what we have now. So we decided, okay, take the mapping, take this thing, put some open source hardware on there, like Arduino and Raspberry Pi, add it with all kinds of features. So if you've seen a Hackerbot demo, there's like 3 little features, like a base, so something that could drive around, a head, not as sweet as this one, but something you could interact with a little bit, and an arm, and it's obviously not as cool as some of the other arms, but something that you could drive around, interact with your voice and with your emotion, and have it do stuff for you. That was the original idea. We said we're going to make a couple of these things. And again, we're not launching, we've just now launched this company, but it's really just an experiment in AI and putting robots on AI. But we just made 4 different models. One that you can just, the very minimum of stuff you need for AI. You do need like a global shutter camera. You probably need time of flights and some sort of sound system. But even with just like this AI one, which is like $200, you could run YOLO 9. So if you've ever used these vision detection systems to track your hand or track a body or track a face or track other things, those can all run and run mobily. So it just does something real in your house. Again, we could reach around and, articulate things and also interact with the face. So I'm just going to show a couple of cool, quick projects that we've made that anybody could make. It's the cool part about these is they're not that complex. I think sometimes what we just saw, and everybody, if you're studying AI and you're in that level, that's pretty cool. But very few people get to have a lot of fun, like with what Alec was doing. That's, so complex. It's so hard for a lot of us to get past that hump and make that work. So we decided we're going to make a few simple projects. One of them is just interactive object detection. If you were out in the demo area, you saw it, just kind of follows faces around. You could have it learn its favorite face. But with this, you can actually honestly perform a lot of your models, run a lot of your AI stuff in just a little head that sits on your desk for a few $100. People like to use it. Often you ask people what they would do with something like this. They say security or sort of these interactive greeting experiences, hospitals, reception kind of thing. So you could see that will eventually come here, but how do you work on that? How do you play with that at home? Well, with something simple and cheap like this. This is another one of my favorites. This is my actual program. So we had like a little hackathon when we first made these to say, hey, what could you make? I made one that does pet aware. So he just drives around looking for my cat. And when it sees it, it'll take a picture. He literally, this is from the robot. He just stood there and stared at it. And I was like, this is the best picture ever. But my goal would be eventually, build something fun that keeps track of these guys and sends me pictures. People always say that, and it seems simple, but it's literally took me maybe 2 hours, 3 hours to make this project. And I'm pretty capable of doing this, but it didn't take, I learned new skills doing this too. So it was like, I'm learning, interacting with AI, and now my robot also keeps itself alive and doesn't run over the cat. Another one that I hacked also was called Sunny Delight. This is just a plant we put on and said, how cheesy would it be if it just looked around for sun? And we made like a little watering thing that it could find water, and it's alive. It's a real live plant that lives in my house. You'll find it in new places every time. So that's what's cool too, is we didn't just like program it, go to the highest sun. It's one of those problems that's non-solvable really. So you just go to some sun. But pretty cool. It's, again, kids could do this if you're like, that's your next step into learning AI and putting it on something that does something in your real world. This is an awesome place to start. You can go pretty advanced from here. Media Buddy is a more advanced one. One of our guys up here was building this. This one will actually drive around, and if it hears or sees media that's known on something like a Shazam data set or something like that, it will either enjoy it or not enjoy it. Those are choices you can make to program it. But the idea here would be that something like this could watch TV with you or with a family member that needs some company, or honestly just kind of being sort of a snarky companion. Pretty cool though. Drive around your house, and when it just gets excited, it sees TV and watches it and say it's like Game of Thrones. It could know what that is and comment on it. So at our next hackathon, we expect it to make some comments on whatever we're watching. But again, these kind of projects only took a few hours. That was our big idea. Time is what we don't have. Time is what a lot of us don't have. And so to be able to run an AI project or just something that you're like, they're usually just on my computer, but to have it move and interact with the real world, that's kind of the whole idea. That's like why we're doing this, is to also make it super affordable. Here's the ultimate one, and this is the one that comes up all the time. Can it get me a beer? Why can it not get me a beer? I would say that this whole thing is a 20-year journey that you're seeing Ian and I trying to figure out how to make a robot get us a beer. We've thought about this for 20 years probably. We built this prototype the other hackathon where it had the beers lined up in like a little thing, and it will go get it. You say, go get me a beer, and it'll drive over and kind of line itself up and figure out if it has the beer and then bring it back to you. Ian was like, that's close, but I'm not loading this thing up at my house, so it's got to be able to get in the mini fridge. So that'll be our next hackathon, is just like a robot that you say, go get me a beer. It goes and opens the little mini fridge, gets a beer out, and comes and gets it to you. The cool part is, again, I could build that. You could build that. Any of us could build something like that, and in a system like this without a, $200,000, $300,000 robotic system, because I think that the ultimate goal would be you get to that system, you kind of upgrade, you learn how to run your models, run YOLO, run Whisper, run things on here that then you're like, okay, now I could probably work on one of these way more complex robots, but these are fun to have at your house. The other thing is, what could you build? That's the whole point of this Hackerbot platform. Build whatever you want. We loved, in our Sphero company, we always had an open API, even for the toys. So even when we had to fight against Disney Star Wars to put an open API in the BB-8 robot, we did it. We always wanted an open API because people were hacking them. People were making them do the coolest things. And so that was kind of this inspiration, is make sure this is all open, make sure it's simple. It does work on ROS and some of these more complex systems, but the idea here is, how can we make super affordable robots that you can run AI stuff on? Like I said, we just started this. This is not a pitch, but what we're doing, Ian and I have both, again, we've sold millions of robots. We do know how to build a company and build robots and manufacture them and sell them. So we're doing this thing called Founders 50. So if you wanted to join us and see how we build this company, how we build these robots, how we engineer it, what's wrong, what's not wrong, supply chain management, basically everything about making a robot that can run AI stuff, join our F50 group. There's like a QR code at the end here. You can join up with us. You can just watch if you're curious to see how it's going. If you join one and buy one, we'll take your feedback. So some people are pretty advanced robot people, some people aren't. Some people are teachers that want to bring AI into the classroom. So we're kind of taking the feedback from everybody to make something that's, again, affordable. That robot that we were demoing is $200. It's like, that's good enough, man. That's cheap enough for me to not have to build it myself. I'm Adam. Thank you again very much. Here's a QR code if you want to get to our website, hackerbot.co. Find me on LinkedIn. I'm super open. I know a lot about robots and a lot about starting companies. So if you want to talk nerdy stuff, I'm here, and appreciate your time today.